which is a Python package. So this we also send around to those who registered before. So in case you're really unfamiliar with FHI-aims, we prepared also a short introduction. So this will really briefly introduce you to the input files, how the I/O works, and so on. So this is like a 5-minute video. Feel free to watch this if this is maybe still slightly confusing to you, or you come from using a different package. The resources, as I mentioned, we are using a cloud server where you have to SSH your way onto it. You should have gotten a username and password that is specific to your account. So please only use those that username and password. It will be done via SSH. So for Windows, it's slightly more complicated, but you should have already gotten a link on how to set up this thing also for Windows. But I will show you this in a second as well on my machine. And then we have 2 nice tutorials prepared for you. So one is on thermal transport, specifically with the Python package FHI-vibes. And this was mainly prepared by Shu, who's also here today. So if you have specific questions related to the material, of course, Shu can also answer. And then the second part will be about electrical conductivity and mobility from first principles. And this was prepared by Jinkai. Jinkai is also here today. We're really happy, and hopefully we have a lot of expertise in case you have also detailed questions later on. So these are the 2 parts. We'll do shortened versions of both just because of time constraints. So, but of course, if you're interested in more details, you want to run them on your own machine later on, feel free to do so whenever. These are open access tutorials you can look at any point. And the important things later on, which I will show you also, is that we prepared the cluster really in the most hopefully straightforward manner for you. So everything is pre-installed. So you don't need to install any Python package. You don't need to install FHI-aims. We prepared already a README, which I'll show in a second with the most important instructions. And you can always look at what kind of calculations you're currently running. So if you're familiar with HPC systems and Slurm, this is really as you would do on any other HPC with Slurm. But we'll try to make it as easy for you as possible. And then lastly, of course, our website. And the main part here, so FHI-aims, as you know, is a material simulation package. All these things are also on the website, which I will try and show you now. So this is really meant to be a hands-on part here. So if you go to our website, which is just FHI-aims.org, you can also directly have a link to online tutorials. So if you go here to the online tutorials, you have a list of all kinds of tutorials, which you can click through on your own time as well. Okay, so I hope until here there are no questions, but as always, feel free to raise your hand, ask them in chat or Q&A, and I'll try to answer as many as possible or delegate to one of the others here from the panelists. So then, if everything is set up for you, then we can start with the first tutorial. This link maybe we post again in the chat, so if some of my other panelists can just post the link for the first tutorial, which is on thermal transport. So before we actually start with the tutorial, and I go through some of the basics here, I just wanted to show you the setup that I'll use for today. So I opened on my machine 2 terminal windows. So you see one, and this will be on my local machine. So I just created a local folder for the hands-on material, because what we'll do is we'll run the calculations on the cluster, but then copy them to your local machine to view the resulting images and whatever. And if you want to look at the results later on your machine as well. So that will be the setup. On my other terminal, I will then log in to our cloud service. So the way to do this is you use the credentials you have received. So in my case, my username was just set to Leon beforehand. Then you need the IP. So this IP is the same for all of you. So if you want to set up, you would just type SSH, your username, which you've gotten in the mail, and then this IP. So I just wait a few seconds for you to get set up, because we want to, of course, make sure that every one of you is on the actual cluster before we start the exercise. And then if you run this comment, you should just input your password, which you hopefully have received. And this is what it looked like. So again, SSH username, your IP. So this works out of the box for Linux as well as macOS. On Windows, you would need a separate setup, which is also mentioned in the registration mails. So hopefully that all works for you. And then you will get an opening message from the cluster. What you can also do is directly look at the module system. So modules here are essentially pre-installed packages from Python to the aims binary that you can just load. So in this case, by default, when you log in, you will have the FHI-aims binary loaded. And you will have here, in short form, vibes, which means this is the FHI-vibes instance or installed version. So as I mentioned, you will not have to install anything. So this is really hopefully straightforward. If you look into your main window here, you will already see several files. So we have a README, which I encourage you to read. That's the point of the README here, because we want to just give you an overview. So as I mentioned, so this is deployed in AWS premises, and we're using Slurm. We've already prepared submission scripts, which are also included on the tutorial pages. But so we have an FHI-aims job, which should be used if you only submit an FHI-aims related job, and a vibes job, which is related to an FHI-vibes job. And these are already both in your directories. You do not have to touch these files. You only, as I will show you, have to copy them in your folders and submit, and that's it. Everything else, as I mentioned, is pre-installed. There is also an outputs folder, which you can, if you just look at this, again, there's a kappa iodide outputs folder. And this outputs folder is really just prepared out of convenience for you. We will do some post-processing for very expensive calculations where we have prepared already the input files. So these should all be in your local folder. So it could be that when you log in, it might take a few seconds for the cluster to actually copy all these files into your home directory, but hopefully this all worked for you. So I hope by now that everyone is set up and the cluster is working. If someone is not able to log onto the cluster, feel free to ask or raise your hand, ask a question in chat, write a question in Q&A or on Slack. So, but I hope everything here is now fine. So then I quickly introduce the thermal transport video. As again, this was prepared mainly by Shu, both input from me and Christian. So thank you again, Shu, for making this nice tutorial. So here we'll talk about the ab initio calculation of thermal transport. You've heard yesterday a lot about the Green-Kubo method, but also Boltzmann transport theory. So this tutorial will briefly introduce both. So you can calculate the conductivity here for an example of kappa iodide, which was also shown yesterday, which I think is a very nice anharmonic example to showcase the differences between the two methods. Everything here is implemented in FHI-vibes. So if you click also on this link, you will also get forwarded to the FHI-vibes repository and tutorials. So if you have any questions related to FHI-vibes, really just click through this, look at this whenever you have time to get some insights. Yes, so this is really the short introduction. There are several sections, and we're really only focusing on the fast track part. So this is really meant to be a short introduction in this tutorial format. If you're interested in more details, so really theory for all three parts, which is just basics phonons, the perturbative approach with the Boltzmann transport equation, as well as ab initio Green-Kubo, so non-perturbative approach. Look through these on your own time. There are quite a bit of details also mentioned here if you're interested. But in our case, we'll just look through the fast track tutorial. And this is, as I mentioned, really the example of kappa iodide. So as I said here, you don't need to look at the prerequisites and the installations and so on. So kappa iodide, you've already heard from Christian, is a quite interesting material. So at first glance, it looks really simple, right? So it's a zinc blende structure, as you can see here. You have your copper and iodide atoms. And then you would expect, okay, this looks to be quite harmonic. But what you will actually see also later on is that this is a highly anharmonic material, where you also have a pretty complicated potential energy surface. So you have local minima around the global minimum, as Christian also nicely showed you in yesterday's talk. So this is actually a really nice example for us to look at, because one, it looks at the surface, as I said, a simple material, but you really have to go to the accurate description of anharmonic effects. And yes, so here. There's actually an interesting also, let's say, physical problem here. So above 643 Kelvin, we know that copper iodide is actually transforming into a superionic conductor. And as we'll see later on, there are short-lived defect structures that can already occur at room temperature, which can be interpreted already as a precursor to this transition. So that's why this material is really interesting from the point of view of describing its thermal properties with the accurate description of anharmonic effects. And the basic workflow we show here is that we'll start with the description of the phonons. So in case you're not familiar with the concepts of really the basic phonon theory, there are longer introductions, but here we really try and make it short. So in the part of the phonons here, we will really just describe it by the harmonic approximation. So that means we expand the potential energy surface or the potential energy just around the equilibrium structure up to second order, and then we neglect all the higher terms. And what you have to calculate is then the second derivative here of the energy with respect to the positions. And this is what we call the Hessian, or sometimes you also call it force constants. And as I mentioned, this is here really a perturbative approach. So you just say this displacement from the equilibrium positions is really, really small. And in this way, we can also exploit the crystal symmetry. So for example, here we have the zinc blende structure. So we actually don't have to calculate a lot of these different displacements. We just have to calculate a few of them. In FHI-vibes, this is all implemented via an interface to PhonoPy. So if you're familiar with phonons, you probably heard of PhonoPy before. Also a Python package, which helps you to calculate these phonons. As we mentioned here, so this is really done so we can quickly calculate some of these results. Please check always the computational settings if you're actually doing any publication quality results. So we'll start relatively simple. So what you can do and how we prepare the tutorial is you can always copy these things to your clipboard. So we'll go, this is all on the cluster. We'll create a working folder. So in this case, I created just a folder, which is just called copper iodide phonons, because we are now creating the phonons. Then for FHI-vibes, to run a phonon workflow, we need two files. So the geometry.in, which is really the format which is specific to FHI-aims. Here, I will copy the contents of this geometry.in file, copy them in, and save the file. And now we have a geometry file. If you're wondering what is this file, well, this is just the zinc blende structure, which I'm showing here. So this is the exact same. Then we create an input file for FHI-vibes. So here we call it PhonoPy-in because we're running a PhonoPy workflow. So there are quite a few parameters here. If you're interested in all of them and really all the details, feel free really to look at the FHI-vibes reference pages and tutorials. They will explain all of these in more detail. So we define, for example, here the geometry file. We define that we want to use the FHI-aims calculator. We define the functionals, in this case, a GGA approximation with PBE sol. We need the forces because we're calculating phonons here. We use a relatively coarse K-grid density just out of having faster results. Light basis settings here specific to FHI-aims. And then we have here the PhonoPy inputs. So if you're familiar with PhonoPy, this should look somehow familiar to you. We have an important quantity, which is the supercell matrix. So this defines how big the supercell should be where you calculate the phonons in. Now you might say, okay, this looks like a rather complicated supercell, but there's actually a longer tutorial which is explained here how we got this cubic supercell. So in the end, this will be just 64 atoms. FHI-vibes itself has already utility functions which just can give you this supercell matrix directly, where you can just copy it in. We have more detailed explanation here and on the FHI-vibes page. And then we have several other things just related to PhonoPy. which I'm sure you can also, again, look at the details on the different reference pages. So what we need to do, we create a second file, oops, which we call phonopy-in, copy all the contents in here, save the file, and now we have two files. And then the next part is where we need to submit the job. For this, we've already prepared a submission script, as I mentioned in the beginning. If you copy this from your home folder, so if you want to always access your home folder, you can put this tilde character in. You type vibes job, and then you copy this to your local folder with this comment here. And then you should have three files. You have your geometry, phonopy, and vibes job. And then all you have to do is submit this on the cluster. So then we just run this comment here, which is called sbatch. This should then tell you the job is submitted. If you look at the queue, you can see, okay, there's someone else already running something, user 66. Hello, user 66. I'm user Leon, so I'm already running a calculation here. It's already running for 6 seconds or so. So okay, I see a thumbs up, so that's probably user 66. You just briefly have to wait. This will finish in under a minute, so you can just submit. I see now more users are submitting. Great job. We'll just wait until these calculations are finished. We should hopefully have enough nodes for all of you to get on queue and then run these calculations. As said here, on these resources, it takes around a minute, slightly less on this system. If you just want to have some details, I mean, this is really a node with 192 cores. So this is already quite a powerful machine here. It's an AMD machine, just so you keep this in mind. And the reason why it takes so long is, of course, now we're running supercell calculations and so on and so forth. So let's check again if everything worked. Okay, it looks like my job, for example, here already finished. So what you can look at is we have now several new files, right, in this folder structure. We have a phonopy folder, right, which is here. In my case, it's always blue if it's a folder. And you have some Slurm outputs because the calculation finished. What you can do now, when the calculation is finished, we can just process the results. And Vibes, in this case, so this is short for FHI-vibes, has a lot of different nice utility functions and output functions to actually do these kinds of post-processing for you. So what you can do is you can copy this comment. And hopefully this is already pretty straightforward. What it will do, well, it will output the phonopy workflow quantities based on the trajectory we just calculated. So we'll just run this comment. And as you can see, it will give you some outputs. So yeah, if you scroll to the top, okay, it's starting this post-processing. It will track, or it will pass all the results, and these results are always stored in this trajectory.sun. So this is a specific format which is used in FHI-vibes. It opens the files and analyzes them. So this is all done via phonopy, as you can see here. It calculates the force constants, band structure, and so on the specific queue mesh we've specified. And then you should now have in this phonopy folder, so I will just briefly showcase this, a new out folder which is called output. If you look at output, you will see a lot of new folders, as you can see here. What we will do is take the current folder that we're in. So that's why I just do here the current PWD is a short comment to get the current working folder. And we'll just copy these results. And this is also mentioned here on the browser page. So what you can do is now I will go to a different tab on my machine, and this is my local machine. So I can just do an SCP comment, right? Remember here, we're using the same comment that we used to log in. So you need the username and the IP. And then you just do a double point. You define the folder you want to copy. So in this case, this. And you can just copy this. You get prompted for your password. You input your password. Then you can see here, there's quite a bit of files, of course, in this output file. So what we're copying here is the output file. If you want, you can, of course, copy the full file again. So as an example, if you instead remove this phonopy comment here, you would copy the full file with the raw files as well. if this is interesting to you and you just want to check it. So now all these are on my local machine. What I can do, I can look at the output and just open some of these, right? So as an example, what we've shown here is the band structure plot with the DOS. So we just open the band structure DOS PDF. This should hopefully open a window. Yes, and as you can see, this is the same plot as on the right. What is important here and why we're doing is we're just checking that the structure is actually in equilibrium and is stable. And what you typically check is whether you have any negative frequencies around anywhere in the band structure plot or the DOS. As we can see, that's not the case. So this is really a stable structure in our context. You can, of course, look at much more, but this is what we wanted to briefly showcase. You have also animations of force of the phono modes, thermal properties, and so on. So this would already be part 1. So I hope this worked for everyone for you. So here we already calculated the phonon band structure with DOS for the specific copper iodide system. We found that it's thermodynamically stable. And now we'll go to the next step, which is we want to get the thermal conductivity. And we start with the simple approach of doing it with the Boltzmann transport equation. So this is really the perturbative approach. So what we do, we can write the thermal conductivity in this theory as shown here. So it's basically you have a sum over the heap capacity of the modes, and you have the group velocity as well as the so the group velocity is here in V, and you have the lifetime of the modes. And from this, you basically then get directly the thermal conductivity. What we need to do here is to account for at least some anharmonic effects as we expand. So if you remember here in the beginning, we expanded to a second order, right? So we have here the Hessian, and now we're expanding to third order. So this is really third order force constants. But as we see, all other higher order anharmonic effects are neglected here. If you need the details again, or you want to read up on these, just click this link. There's a more detailed description also. So what we do is then we start with the FHI-vibes approach and the BTE. So we go back. We create a new folder. So what I'm doing is I'm going back one directory. Oops, sorry. Let's run this here again. So we have the proper folder. So if you run it in copper iodide phonons, you will go back at a directory. You create a new folder, which we call just thermal BTE for copper iodide. And here we'll do the work this time. Essentially, we do the same thing as before. So we need 2 files. The input is, of course, the same. So we just copy this input. And we create now a phono3pi.in, right? And just copy in the results here again. The content that we had previously. It looks quite similar, so it's still PB solid, still light, same K-point density, slightly higher supercell matrix, so it's essentially 3x3 supercell with some cutoff and so on. So it's still similar. If you're interested, there's a more detailed description also here when you click on this perturbative method section. If it's really of interest how you do the specific stuff. Now keep in mind, if we would do this calculation, it generates 102 display structures because we're going to third order. So when you go to third order, in this case, you will need a lot more structures to actually calculate the full third order force constants. Just submitting this calculation would take too long. So this would probably take an hour or so with the current setup we have. So instead, we already tried to give you all of these results. So what you can do is you can copy the results from your local folder by just copying this comment. This should work, hopefully. And then you just look at the file and then, okay, now I have the phono3pi folder, which is where your results are in. So it looks very similar to the previous calculation. We just here now copy in the results. And if you look at the folder, just briefly, you will see you have the trajectory file. And that's the file you actually need to do the post-processing. So we copy the vibes comment now. We do the same output analysis and post-processing, but we are now using phono3pi for 3pi because of third order. So we do this. Again, it gives you some some output. Keep in mind here, this would take a few minutes. Why? Well, we have now, of course, over 100 different structures. So it takes a while to actually go through all these structures, calculate, again, all these constants on the Q mesh and so on. So just, yeah, wait a bit. It needs to map all the tables and whatever. We can, of course, use this time in case you have any question now or comment. So if maybe, I don't know, something is not is too small on your screen or so, I can still fix it while we wait. So is there any question from your side to what we're currently doing? So feel free to raise your hand. If not, then of course we don't need to. At least in Zoom for now, I don't see anything. Okay, we can see we have a few users running FHI-vibes currently. If you're struggling with the setup or so, just let us know. Of course, if you're a bit slower, no worries at all. Just do it in your own time or in your own pace, I mean. Otherwise, we're of course here. So I think there was already an answer in the webinar Slack, which was answered by James. So thank you. If you have any questions there, you can of course also ask in the Slack channel or here in the Zoom. So, but again, don't be confused why this takes a while. This takes a while because we have so many structures that are being post-processed. So this is normal. Okay, now it looks like it was able to do the mapping of the force constants. And as you can see here, it looked at the trajectory in around 2 minutes, 24 seconds. And now if you look at the PhonoPy folder, a Phono3Py folder, sorry, we should see we have an output folder. Right, so this worked. So next, as also described here, we'll go into this output folder. And then, because what are we interested? Well, we are interested in thermal conductivity. So PhonoPy already has a nice workflow that calculates now the thermal conductivity with the Boltzmann transport equation based on these force constants we've just calculated. So you just run this comment, which copied here, right? We have a mesh value, as you can see here, which is just called minus mesh 666. The mesh parameter is the K-point density where the phonon scattering events are calculated. So this is not a converged value. And I just want to point this out. As we see later on, you really have to go to something like 20 times 20 times 20 to get the converged value. But this will just take some time to post-process. So instead, we'll just do a simple 666 grid. If you run this, you will see the Phono3Py output terminal, and it will just run this comment. After a while, just wait for a few seconds, you will see some output. Okay, it got the supercell matrix correct. It's reading in the force constants, so both the third and second order force constants. And now it calculates the scattering events on all these kinds of grids, right? So unfortunately here, my window is a bit big, so let me a bit small. So if I just briefly fit this all on one line, what you see here in the output, you collect all the collisions, right? And now you directly get the thermal conductivity in watt per meter Kelvin for what they call here is the tetrahedron method. So that's just the interpolation scheme. And then you get the values in terms of temperature in each of the directions. So as you know, this is an 3x3 tensor matrix in this case. So we have x, x, y, y, z, z, which are the three main directions. And then we have the off diagonals. what would you expect from the structure? Well, we're looking at a zinc blende, cubic structure. So if everything goes well, the three main components are the same. So x, y, y, and z, z, z by symmetry should be the same, and the off diagonal should be 0. And as you can see here, this is nicely done. Because why? Well, in the beginning, we're using already the symmetry information from the cell. So that's why we get the correct symmetry out. What we're interested in here is more or less room temperature. So we can scroll down to, let's say, 300 Kelvin, and this is what we see. So we see a value of around 4.491, and this is again the same as we see in the tutorial page. So now you know, okay, from this output, which are also saved in this HGF5 format, by the way, you get your thermal conductivity. We find it is around 4.49 watt per meter Kelvin at this Q mesh density. If you actually go to higher meshes, the thermal conductivity is much higher. So converged values would be around 5.9, so almost 6 watt per meter Kelvin. Now, the important part here is, compared to experiment, this is not so nice, right? So experiment, you get around 1.7 watt per meter Kelvin. So the overestimation is huge. So we overestimate by more than 350%. And the reason I already somehow described in the introduction. You really have, in this specific material, carbide, you really have to include all orders of anharmonic effects in the calculation of the thermal conductivity. Otherwise, you drastically underestimate the actual value for the thermal conductivity. And as I'll show you here in the next section with the Grün-Kubo approach, they are also very, let's say, when we look at MD trajectories in the following section, you will see that the phonon picture that we have with in these systems, you can describe the phonon effects with just small perturbations. This completely breaks down. So, and this is what we'll see in this section here. So, yeah, I'll just give you a few seconds to catch up in case you're still running something. Let's take a quick look at the queue. Okay, so the queue is empty. So this more or less means at least all the phonon calculations from before are done. You might still be waiting on the post-processing. So I'll just give you a few seconds. If you have any questions here, please ask them in the chat. Again, raise your hand if you like, or yeah, use whatever means you have available to reach out if there's any issue. And then I'll continue in a minute or so. Okay. So it looks like for my colleagues, there's not much FHI-vibes being run at the moment. So that basically means hopefully that you are done with this section. So we'll continue with the other part. So what we've seen already is, so we looked at the phonons, the structure is indeed stable at this temperature, right? Then we look at the thermal conductivity with the Boltzmann transport equation, and it includes some anharmonicity in a perturbative way, but it's still not nicely matching experimental values. So that's where we go a step above. And what we'll do here, and this is, I think, what Christian nicely illustrated yesterday, is the Green-Kubo approach. So how can we include anharmonicity? Well, in principle, you can also include higher orders of anharmonicity in the expansion of the potential energy surface. What you can do instead is you can also just do ab initio molecular dynamics. And if you do the molecular dynamics, you don't do any approximation, right? So your potential energy surface is calculated in full, and you directly include all orders of anharmonicity. And this is really non-perturbative. So you can have huge displacements in the cell, which you will just get naturally with molecular dynamics. So what we can do is you can do a long molecular dynamics run. You can look at the heat current. So this is here, this J, which you can compute. And you can compute the time autocorrelation function of this quantity here. And from there, you can estimate with the Grün-Kubo formula, or you can get the thermal conductivity. You do this essentially for different temperatures, right? So in our case, we're looking at 300 Kelvin over some time. So in principle, of course, you should have as long trajectories as possible. In practice, this is always limited because you have limited computer time. What you can also do, and this is what we'll show later on, is to somehow get some statistical sampling. You can just run several independent MD runs of the same system at same temperature and just average over them. And if you average over these different trajectories in the end, you also get an uncertainty estimate and you get hopefully good values. So in practice, typically, it still needs to be determined for each specific system how long the MD trajectory should be run. In this case, the MD trajectories were run for around 60 picoseconds. Yeah? And these trajectories are from here, reference 4. So if you click here, this is the reference from Florian, which was also shown yesterday in the talk. So feel free to look at the details. So this will also describe again how these MD trajectories were calculated. It's all the same functions. So these are again PB solved because of course you want to have the comparison to before. And I think these are also 200 something atom supersets or so. So these are quite big calculations in this sense. And instead of you having to run these calculations, of course, we've Florian nicely already prepared these calculations for us. So we create here again a new folder, right? So now we have what we call kappa iodide underscore GK. So that stands for green kubo. And then we just copy in a trajectory that we already prepared for you. So in that's this outputs folder I showed you before. You can just copy in the NVE trajectory. And then you see this folder here. If you look at the folder, you will get a summary PDF and a trajectory in NC format. So this is the net CDF format. So this is what FHI-vibes uses internally to save positions, velocities, whatever heat flux and so on, all kinds of quantities you get from your MD simulation. And keep in mind, all these MD simulations are run internally with FHI-aims. Right? So this is all based on FHI-aims ab initio MD trajectories. So we are in this folder. What we can look at, get some more details on this trajectory. So what you can do is you can use another utility function, which is just called vibes info MD on this trajectory file. And then you'll see some first information, right? So it summarizes some displacements. Already interesting just by looking at it. There are some displacements which seem to be huge, right? So you have displacements of almost 3 angstrom. So that somehow already tells you, okay, it looks like the perturbative approach here might not be so nice anymore, right? Because these displacements are clearly not small displacements anymore. It gives you a summary on the forces, on the temperature. So in total, you ran, as I mentioned, 60 picoseconds, which is 12,000 at one step. On average, the temperature nicely fluctuates around the 300 Kelvin that we want. You get some information on the pressure and so on. The mean energy drift, which of course here is quite small as we would like it to be, because this tells you the quality of the MD trajectory. And then now it looks okay. We have the trajectory. Then we can just run the green kubo workflow. This is all integrated into FHI-vibes. So what you only need to do now with the newest version of FHI-vibes is run vibes output GK on this trajectory. If we do this, it already calculates some of the things. So it runs the green kubo workflow. It calculates some prefactors. It estimates some filter windows for this autocorrelation function and so on. So this is quite complicated from a technical side, but all explained in the references, which are also linked at the bottom. So this is these are the 2023 papers by Florian as well as the 2020 paper, where he explains the anharmonicity measure, which I'll come to in a second. So, but the important thing here is this is all, of course, done automatically. So you don't really have to usually tinker with this at all. But what you will see is the kappa value, right? So this is the average kappa value. And we have also the full 3x3 tensor for kappa. Now, these are, of course, just text values. You can also plot all these things. So if you just run this comment here, which is vibes info gk minus plot, it will create some plots for you as well. So if you take a look now, you can see there are some PDF files which appeared, which is the green kubo summary. This MD summary we already had previously. So what we will do now is again copy with this SCP comment the results in our new folder. So let's do a new folder here, which we will call kappa iodide GK. go into this folder, and then copy, oops, sorry, of course I have to adjust my username and IP. Again, same as before, username and IP, and then you get the folder. You can actually copy this directly in. Oops, sorry, this is on Mac, so I need to put some quotes here. You will be tempted or prompted for a password. Include the password once again. This will copy your PDF files, and then you can just open your PDF files. So let's see here. I'll open the green Kubo summary, and this should hopefully be the same plot. And as you can see, it is. So what you see is two subplots, right? So the top plot is the heat flux autocorrelation function. So all the thin lines is just the raw data, right? And it looks maybe a bit noisy, right? If you look at all these lines, the wiggles and so on. And the thick lines is really the post-process data, right? So there you remove the noise and fluctuations, which are actually not part of the thermal conductivity, right? These vertical lines here, as also mentioned in the text, is somehow the earliest indication where you cross the x-axis, right? Where you cross essentially the zero threshold. We assume that the autocorrelation function up to this dip, right? So for example, up to here, or up to here for the different directions are accurate. And then, yeah. And the thermal conductivities that we report in the output previously are always integrated up to this time. So for Y, integrated up to here, integrated up to here for Z, and integrated up to here for XX. And then in the end, in the bottom panel, we just then have the thermal conductivity, right? Where you have the different directions in the different colors, and you have in Z the mean value average over these. Now, if you noticed what happened before, right? We mentioned in the BTE case that all these three components should be the same. Judging from the output, this does not seem to be the case. Why is that so? Well, here we are really just running MD for a limited amount of time, right? So we are not running this MD for, I don't know, instead of picoseconds, I don't know, thousands of picoseconds, whatever, right? To really get converged trajectories. So there will always be statistical fluctuations. And that's coming back to what I mentioned in the beginning. So that's why it's recommended, don't just run one trajectory, always run multiple with different initial conditions. And then you can get statistically average results in the end, which then should be, I mean, at least when the MD is somehow long for each individual MD run, this should give you reliable results. There's one thing which is not shown here in this plot. So this value we should not trust yet. Well, why? What we are calculating these results in is in really small supersets, right? The reason is, of course, we can't really afford thousands of atoms with ab initio in D for 60 or 100 picoseconds or so, right? Instead, there's a workflow to calculate the interpolation to essentially infinite size with this finite size extrapolation scheme, which is done in frequency and reciprocal space. Again, quite technical, but also mentioned in the paper if this is really something you're interested in. So what you can do, you can just run the output, and then you say, okay, but I want to include the interpolation. So here you just do the interpolation. We copy this and just run the file. It does the same thing as before, but now you see there's some new stuff happening, right? So here, for example, it looks at the supercell and primitive cell, right? It looks at the Q points, it reduces the Q points with symmetry, looks at the force constants. So these are all included in a trajectory file, right? So it can just use them. It fits to some exponential for the lifetimes and so on and so forth. So of course here it's quite a bit of output, right? You can see in the end, we have 4 new PDF files we can look at. So what we'll do again, go over here, copy in with the same comment as before your PDF files. Again, you were prompted for password, put this in. And then you can see here, you get all these PDFs. And then open the one that is shown here. So in this case, it's the interpolation fit, which is the most important. And this is really what gives you the results for infinite size. So here we are really looking at it of the kappa, also the thermal conductivity over size, right? And that's interpolation you essentially do. So number of Q points in this case. So the green value is actually the one we calculated, right? All the other ones is the extrapolation. So all this is done based on the force constants and so on. I think it's essentially similar to the BTE approach, as also mentioned here. So you evaluate the BTE for the thermal conductivity, and then essentially use this interpolation to get the final extrapolated value with infinite size, right? What you then do is you use this finite size correction you get from the BTE, and then add it on top of your final finite cell results, right? So you get your green Kubo kappa, you add the extrapolation finite size correction on top, and this is essentially this value here. And if you do this, you get something which is shown here. It's also shown in the output, I believe. Yes. So if you look here, you get now new values, right, which are called corrected kappa. So that just means you get the finite size corrected thermal conductivity, right? With uncertainty, you get the full tensor and so on. Feel free to take a look at some of these other plots. They're, as I said, quite technical, but if this is something of interest to you, feel free to, of course, have a closer look. You can do the same exact procedure we've done here for another trajectory that we have prepared. So if you actually do the same thing for what we call NVE.2, that's the second trajectory, it's the same system, just different starting conditions. It's again 60 picoseconds, but it's just not the same run. I skipped this here, but you can do this if you like. You will get a value of around 2.1 plus minus 0.4. So it's quite a different value, right? But if you average over them, you get something like 1.9 plus minus 0.27. In the paper, I think it's actually averaged over 3 trajectories in the end to get these kinds of results. But what you see in the end is where you get a value of 1.9 plus minus 0.27. And this is remarkably close to the experimental value, right? If you remember, we saw it 1.7. So this is really from the chemistry handbook. This is really the reference result. And here you can nicely get very close to experimental value. And the reason is shown here. So you run along MD trajectory and you see a plot something like this. So what we plot here is the what we call the anharmonicity measure. So this was also introduced by Christian yesterday. A value of 0 just means this is a perfectly harmonic system. So 0.5 already indicates it's quite unharmonic, but then there are sudden jumps which spike in very huge values for this anharmonicity measure. So they go above 1.0, for example, here. And what happens is you have temporary defects forming. So in this case, you have kappa interstitials forming in this kappa iodide. And these are relatively short-lived, so around 10 picoseconds, and then it goes back to your original structure. So what you see is if you go along this potential energy surface, you don't just sample the global minimum, you also go into local minima. And you actually have to sample these local minima to get accurate thermal conductivities. So it's really important. And now it's somehow clear why the perturbative approach doesn't really work here, right? Because this deformation, or let's say this formation of the interstitial can't be anymore described by any perturbative approach. And that's why, for example, this Frenkel defect is one of the reasons why in kappa iodide, the harmonic approach just breaks down. And yeah, so here, this was a short tutorial to show you how we calculate from start to finish the thermal conductivity, both with the Boltzmann transport equation, but also with the green Kubo approach for this very anharmonic kappa iodide system. And this was all done with FHI-vibes. And as I mentioned, in the backend, we all used FHI-aims raw data. So I hope this was, yeah, so this was the first tutorial. I hope this was already interesting to you, and maybe you're still running some of the post-processing here. Are there any questions concerning this point? Or any comments or the like. Nice, some claps from the audience. Thank you. I think at the moment I don't see any. I'll briefly wait, maybe a minute or so. Just, I mean, feel free again, as I mentioned, to copy all this raw data, right? So if you want to look at, if you want to look at this in your own time, so you can copy the phonon folder, the green Kubo, and the thermal BTE. Keep in mind, of course, the disk size for the green Kubo is a bit bigger, right? So it's like 300 megabyte here. So keep this in mind. All these are also linked in the tutorial page on a GitLab repository. So if you want to download this in your own time, there's also a link here where you can download these trajectories and some others, I think, also. Okay. Then questions or so, I don't see any. Then let's do the second part. And for this, also go back here. So this was thermal conductivity. As I mentioned here, there's more to it, and of course, many more details. If you're interested, just look at this. The second part we wanted to briefly show you is the Kubo-Greenwood formula. So this is implemented rather recently. So this was mainly work done by Jinkai. Also, this tutorial was mainly prepared by Jinkai. So thank you again, Jinkai, for implementing. So you should use a relatively recent version. We also released, I think, a patch version a few days ago related to some things on this ab initio Kubo-Greenwood formula. But now it works within FHI-aims as well. The link, I think, will be posted again in the chat, just so you can open the web page here. I think this should hopefully be done soon. Yes, I think now. Yeah, perfect. So James, thank you, James. Posted the link already. So the Kubo-Greenwood approach here does several things, right? So you can calculate band type conductivities, but you can also calculate mobilities. There's some part on the theory, so we don't really want to focus on the theory right now. It was briefly introduced yesterday. If you're really interested, there is a paper which is still I think it's in press currently, as Christian also mentioned. So if you're really interested, just feel free to have a look at this relatively recent paper where all this is described in much more detail. But again, here in this case, everything is set up for you as well. So here you don't need any separate like FHI-vibes functionality. So this is all integrated in the aims code. So what we'll do is we'll actually do the first part, which is the optical conductivity of aluminum. And the other parts, feel free to just do the post-processing whenever you have time. So for the optical conductivity, just to give you an idea on how to do these kinds of calculations, right? So we calculate the conductivity here of an aluminum cell. So this is just FCC4 atom aluminum at very high electronic temperatures. The reason is, I mean, 1 eV, you might think, okay, that's extremely high. Yes, it's one of the, I think, well-established reference results where people test the green Kubo approach for. So that's the reason we are looking at this approach here. And what we'll show you is the dependence on grid size. So whether you use a relatively small K grid of 6 by 6 by 6 or larger ones like 18 by 18 by 18 and so on, to show you also an idea of how well this converges, right? So we start relatively simple. So we start with a 6 by 6 by 6 K grid. Just create that folder and go into that folder. And now what we need to do is create a geometry file. So again, you just have the geometry file with the 4 aluminum atoms. You put them in, right? If you like, of course, we can also visualize this thing here with GIMPs. So GIMPs, as some of you might know, is a graphical interface. So GIMPs can do a lot of things like look at structures, build structures, create control files for FHI-aims, analyze output, give you workflow. So essentially templates if you want the band structure, if you want to do GW and so on. So GIMS will post it in the chat just so you know. Is something you can always use to look at input and output files for FHI-aims. So to get back here, so we have the geometry file. Now we want to create a control file, right? The control file in FHI-aims, in case you're not super familiar with this, as I mentioned in the beginning, we have a short introduction video, but we hope that this is relatively legible. In the sense, we try to make all the inputs that you have to put in the control file relatively verbose. So, for example, here, the exchange correlation you just define as PBE, right? The relativistic correction, for example, here is just atomic Zora scalar. So all these things you already probably know from different codes. You specify the K-grid. So in this case, 666, as we mentioned. And then you specify additional things. So the occupation type here is what I mentioned in the beginning. So we want to simulate this thing at a relatively high electronic temperature of 1 eV, right? Which is what you specify here, which is occupation type. In this sense here, it's a Fermi distribution. Then you run the Kubo-Greenwood workflow, right? This is explained somewhat in more detail here, so you're also familiar with all these, what all these things mean. So you can do a broadening. So for example, here it's 0.06 is the width of the broadening function that you do when you get your spectra in the end. And all these different inputs, which might look at first glance quite complicated, but they're all somehow explained here. So you have an energy window which you define, which is just defined by this range of, let's say here, minus 20.5 eV to 9.44 eV, which is always related to what we call the FHI-aims internal zero, where you calculate the momentum matrix elements. You have a range of where you want to calculate your optical conductivity. So on what frequency range? So in this case, you want 0 to 5 eV, and then we want 2000 steps. And then in the end, what do we want? Well, we want the average conductivity over all the coordinates, which we specify here. If you're interested in all, let's say, input parameters you can use and so on, this is also part of the FHI-aims manual, which we'll try to describe in much more detail. So, of course, if you're interested in something now, we have also the expert here. So Jinka is here as well as Christian. So they can, of course, tell you some stuff about all these different parameters. And then we have this option of the Kubo-Greenwood width function. So this essentially defines multiple broadening parameters. So if you know and calculate the spectra in the past, this just indicates we want 10 broadenings between 0.01 and 0.1 eV, by default done with the Gaussian. So do you need very sharp peaks? Do you need more broadened peaks? What are you comparing to and so on? So this will depend, of course, on your workflow and what you're looking at. And then we typically can also, this is also within FHI-aims, you can specify Fourier interpolation. So while your SDF grid is done, for example, on 666, if you increase the DOS K-grid factors in the post-processing step, you can actually increase the K-grid. So instead of doing like 666, you can do essentially 18 by 18 by 18 with a Fourier interpolation. And how this converges or how this compares to actually running on 18 by 18 by 18 SDF grid, you'll see down below in a second. And in the end, what we always have to do in this control files is attach the species default. So species default in FHI-aims is the basis set. So this gives you the basis set. Of course, for you, you can just run through these steps, or in this case, out of convenience, I would just copy the full file. If you copy in the full file, yes, you will see this is the file. Again, it's basically the same as we mentioned before. Has some more comments on what all these different parameters mean, the width, and so on, K-grid factors. So you have your control file. Now, what do you need to do? For FHI-aims, you only really need two input files. It's a control, so that controls all the computation parameters of the calculation, and you have the geometry file, which controls what kind of system are you simulating. What you need on the cluster, of course, now is the oops, sorry, I made a mistake. Which I just noticed now. but I will just fix this. Okay, I'm not sure what's going on with my terminal. Second. Sure why my enter is not working anymore. Anyway, let's try to do a new profile view. Sorry, this is of course always the what we call in Deutsch the Vorführeffekt. So when you showcase something, it never wants to work. So let me go back to the folder really quickly. This is what I call hands-on conductivity. Yes, tutorial 1. So what I forgot, of course, is this should not be done on your local machine. So that was my mistake. Of course, we want to do all this on the cluster. So let's copy all this into the cluster. And then we actually go back to the cluster. So sorry if someone did it also on the local machine. Of course, we want to do calculations on the cluster. So what we'll do here is we'll copy the submit script, which is now FHI-aims job, right? So before we had vibes job, but now we're running just pure FHI-aims. So that's why we have this job here. Then we just S-batch, so that means we send it to the queue. You can see my job is running. There's something else running also, user 66. But this is really, yeah, this should be relatively fast. Just wait a few seconds. More people are submitting. Yeah, see, as you see, it's already done. And now you get quite a few files. In case you're wondering, how do you check if an aims calculation is finished? You just open the aims.out. So that's the by default, or that's what we call the output here. And if you scroll to the end, you see some output. And if you see have a nice day, that typically means it all worked out fine. So here we see this calculation finished. And now we have a lot of different files. So specifically from the Kubo Greenwood approach, you see KG files, right? So you always see the output for the Onsager coefficient here. So that's the conductivity. And you always see the output here for the mobility, right? The 0.01 and so on, if you remember, that's the broadenings we defined. So we defined a range of 0.01 to 0.1. And this is something you can just visualize out of convenience for you. So if you look at one of these files, so let's say, for example, let's look at just the conductivity for 0.06 eV, which is averaged. It seems quite busy because, of course, there's a lot of information in here, right? But essentially, if I increase this window, I can't quite fit it all into one, but hopefully you see it somehow. So the first entry here is the frequency, right? And this is just given in EV. And then we calculate all the contributions to the electrical conductivity, right? So you have interband transitions, you have intraband transitions for electron and hole, you have both band transitions for electron and hole, and then you have the same split up into interband transitions for the hole, intraband, both bands, and then again the same for the electrons, right? So that's how you can somehow have an idea how these results are interpreted. And then feel free to have a look at these lines in some more detail, right? So here it's also explained you have the carrier density in the second and third lines of electrons and holes. And the first number is always total number of free electrons and holes in the simulation cell. So that's basically this entry here, right? Yeah. And then you can look at all these different conductivity measures. So the value is always, or the unit is always the same. It's always ohm it's 1 over ohm times centimeter. Yeah, there's some more details here if you're interested in all these different columns. As also mentioned here, So this is relatively new functionality. So what has been thoroughly tested is the interband contributions. So that means essentially columns 2, 5, and 8. As you notice in the plot, there's in the file, there's also intraband and both bands, or both contributions. But these have to be benchmarked in more detail as well. So for now, we're focusing on 2, 5, and 8 for the columns here. So what we do then is we visualize the results. For this, you can just write a simple plotting script. So that's what we've done here. So it uses NumPy and Matplotlib. You read in the file you want. So in this case, we're just reading in the 0.060 eV broadened output for the conductivity. So we create a plotting script. Plot conductivity K666. Copy in these contents, right? Here, for example, here we still convert, for example, from centimeter to meter and so on, but it's all not too some minor details. If you just run the script now, it just runs for a few seconds and you should get a plot. This, of course, we can copy back. So if I now go back to my local folder, yes, I can SCP. Again, always need the IP. On Mac, you typically need these quotes. We copy this in here. We copy the password. Should take only a few seconds to copy all the files. And then you can open the conductivity output, which is just called here conductivity underscore K666. And then you get essentially the same plot as here. So you get the conductivity, electrical conductivity over the frequency range, right? If you compare this, so this thing here is the spectra which you can find in this paper, which is linked here, so KGEC is a separate code which compares their result also to an output from Abinit. So it's the same K-point density, it's the same system, aluminum, 4 atoms, 1 EV electronic temperature. And as you can see, it's really essentially a very similar plot. So the peak amplitudes are slightly different. There are some differences here in the low frequency range. So if you compare here and here, but overall, this is very similar. Of course, these are all different, right? These are different codes, different basis sets, different functionals, different broadening potentially, and so on and so forth. So this is quite, yeah, it's not a one-to-one comparison in that sense, but it correctly reflects the spectral shape. Then we do the same thing we just did instead of 666 for a slightly larger cell. So now we go back, we do Fourier interpolation, right? So what we do in this K18 by 18 by 18, we copy in the files we had previously. So now we have a control and a geometry file. And the only thing we change, as I mentioned in the beginning, is those K-grid factors. So we still calculate the SEF grid on 6 by 6 by 6. We just increase the density of the K-grid factors, meaning any post-processing, like here, the Cobo-Greenwood approach is done on a larger grid than the SEF. And we do the same thing again for comparison now on an SEF grid of 18 by 18 by 18. So again, copy in all these files. You just have to follow the instructions here. And then we change the control file now by increasing the SEF grid. And then essentially you just have to submit the 2 calculations. So we copy in here an FHI-aims job, we submit. We do the same for the for the K18 by 18 Fourier interpolated one, copy in the FHI-aims job script and submit. And then you can take a look. As you see here, I'm currently the only one running. So I have 2 jobs running on the queue. In this way, you can monitor. They're both relatively quick because, of course, this is a relatively small example. Briefly wait. So there's one still running for a few seconds. And here I can briefly explain essentially what we are trying to do. So now we ran a calculation on a larger SCF grid or on an interpolated grid for the post-processing. And we just want to visualize and show you the difference. Okay, everything is done on our side. So what you can do is you can just use this plotting or create this plotting script. For that, we go one folder structure up. We create the file, we copy in this Python file. So essentially is what we're doing. We're reading in two files, one from the Fourier interpolation, one from the SCF, and we're just plotting them together. If you do this plotting, it will, you only need to wait a few seconds. It's still, let's see, where is it saved? It's saved in conductivity exactly here. So if we copy this file, or if you get the path to this file, you can copy it back to your local folder. Again, it's always the same workflow, IP, define the file, copy, password, and then open the plot. And then you see a plot, which is this one, right? So we're essentially plotting the full grid spectrum with the blue dots. Of course, here, keep in mind, this is just, this is like the actual frequency dots and so on. You can, of course, draw a line through it if you like. And underneath it, we have the Fourier interpolation, right? So you don't actually have to do all the full SCF with the full grid. You can do the SCF with something like 6 by 6 by 6 in this example, and then just do the Fourier interpolation on top, right, for the post-processing. And this can save you a lot of time. So of course, in aluminum, the system is relatively small, so it does not make much of a difference. But of course, if you go to much larger systems, this really makes a drastic difference. And that's what we wanted to showcase here. So the implementation can use Fourier interpolation for the finer spectra as well, without really any loss in accuracy. And yeah, as we mentioned here, of course, the SCF grid is still, of course, converged. But in this case, it's no problem to run 6 by 6 by 6 and then run a much higher density for the post-processing. And that's essentially what we wanted to briefly showcase for the optical conductivity. You can do the same thing later on for the mobility and so on. So this is not part anymore of this tutorial now. And the main reason is this is a bit more involved. So what you do is for the mobility, you typically do some sampling at a temperature. You create different samples of your structure, and then you run essentially FHI-aims for each of the structures, right? And to actually get converged results for all of these different systems, you typically need also bigger supersets, which is why we are skipping it here. But feel free to have a look. If you always scroll down to these pages, you also see we have the solutions, and the solutions in this case means the output parameters, the output files and so on. And the post-processing, so you can download this to your local machine, have a look. You can look at what, for example, the Drude fit is and so on. And the same for strontium titanate. This is the example in the paper that I've already mentioned in the beginning. It again goes to all the parameters that are needed here. And in the end, you get the Drude fit over several samples and so on. So that's essentially what I wanted to show today in terms of the tutorial. So I hope this was helpful.